I really appreciate your time. I'm very much looking forward to your presentations.
Thank you very much, Dr. Chang, and every one of you for giving us your time and also the opportunity to talk to you all today. I am Senthil, founder CEO for ONS Bio LLC, a life science vendor based out of Cleveland area in Ohio. So I'm joining from Ohio. And today's talk is part of an active outreach to researchers and clinicians such as yourselves across the US with the goal to educate and create awareness about the potential for bioprinting as a technology to transform and advance your research. Now, this is done as a partnership effort between ROKIT Healthcare, my company ONS Bio, and Indicate Technologies from the West Coast, based out of Santa Clara, as distribution partners of ROKIT. Now, ROKIT Healthcare is a South Korean pioneer and leader in regenerative medicine. Notably, ROKIT Healthcare is the manufacturer of 4D bioprinters, organ regeneration platform technologies, namely the INVIVO 4D and 4D6, which have revolutionary potential and applications in both basic and translational research, and also in the development of autologous stem cell and tissue-based therapies. It's very important to note that ROKIT also manufactures industrial 3D printers and also offers genomics and single-cell RNA services alongside what they do with respect to bioprinting. Today, I'm joined by my colleagues, Dae Lee from ROKIT Healthcare, joining us from Seoul, South Korea, and my colleagues Chris Kamimura and Parker Bowenberg from Indicate Technologies, joining from California. So together we make up a team of bioprinting and 3D printing specialists that you can always refer to for any on-demand support anytime. So about the presenter, Dae Lee will be the presenter today. Dae is a senior bioconsultant and bioprinting expert, and she is the Global Business Development Manager at ROKIT Healthcare. She is in charge of business development and oversees dissemination of knowledge and research service platforms that bring 4D bioprinting technologies and computer-aided design and biomaterials together to offer a breakthrough in research and provide medical solutions. Before joining ROKIT, Dae was a research assistant at the MIT's Koch Institute of Integrative Cancer Research and the Brigham and Women's Hospital, Crohn's and Colitis Center. And she has experiences both at the bench and in clinical trial coordination. She has a BA in biochemistry from Smith College in Massachusetts, USA. In the interest of time, I want to make a point. Please save your questions that you may come up with during the talk to the end of the session. You can also save them by typing them in the Q&A chat, and we will have your questions addressed at the end. So without further ado, over to the speaker, Dae.
Hey, everybody. Thank you so much for your invitation to have us, ROKIT Healthcare, and our partners, ONS Bio and Indicate Technologies, be present here to talk about the values and benefits that bioprinting technologies, we believe, can make in your research and your works. My name is Dae, as Senthil already introduced, and I am a senior bioconsultant at ROKIT Healthcare, and my role is to help researchers and scientists learn more about how the bioprinting technology is being applied in real life today and how it could potentially apply to your own research works, both to reduce time and to boost the effectiveness of the research models that you're using. So ROKIT Healthcare, in short, is a company that focuses on especially the technology of 4D bioprinting to create architecturally complex and functionally more meaningful models using human cells. And in one short video, I'm going to show for you what a 4D bioprinter may look like. So I'm going to talk a lot more about what the bioprinting technology really is, but before I begin, I just want to once again acknowledge that we are proud to partner with ONS Bio and Indicate Technologies for all technical support in the field of bioprinting and 3D printing in general in the US. And Centil and Chris from the two companies with me make up a team of bioprinting and 3D printing specialists. And you can refer to us for any on-demand support and questions. And today I'm going to be focusing on, as per the interest of your department, about the values of bioprinting human skin tissues, especially in the context of today's megatrends that we find throughout the worlds of science and healthcare. And also talk about the real-life applications of what these bioprinted skin tissues mean in science and healthcare. And beyond the basics of the bioprinting technology, I'm actually going to cover case studies and journal publications about how these bioprinted tissues are being used across in vitro and in vivo modeling. And we'll actually be taking a look inside not only the research labs, but also in commercial industries, as well as in the operating room. All right, so let's begin. First and foremost, it's important for us to understand what is the meaning of the human skin equivalent in today's era of science and healthcare, right? What is driving the need and use of such model? Well, there are several megatrends in biomedicine that give us reasons to innovate in the area of engineering human skin models. First and foremost, as we all know, is the global trend of the animal testing bans that has started in Asia, but is now actively moving across Asia and now in the Americas. And amidst this wave of change, the cosmetic industry is a part of the industry that has been most significantly impacted. However, it's not the only area of research. It is going on to impact pharmaceutical industries as well as normal common household goods or chemical development industries. And engineered human skin equivalents are now in the spotlight really as the more humane and effective ways to replace animals in the testing of these new compounds. Second megatrend is, of course, the need for better human physiology and disease models, which has come with the understanding that animal models and 2D skin models simply don't recapitulate what actually happens in the human body. Many studies, some of which I will go over later on, have been done that demonstrated that chemicals which are non-irritants in an animal model like the rabbit may end up being irritants on the human skin. And studies, especially in cancer, have shown that 2D cell cultures tend to be less resistant to therapies than 3D cell cultures, leading to skewed decision makings in the evaluation of novel therapies, therefore requiring better models in terms of the human skin equivalents. And finally, this of course leads us to the third reason driving the need for better human skin models, and that's the need to save the time and costs of R&D. And annually, it costs about $2 billion to bring a new drug to the market, but this number has actually doubled from $1 billion that it cost back in 2010. And the R&D costs are going up each year, but ironically, the healthcare budgets of each country are becoming more and more strained. And the only way to resolve this dilemma would be to create a fully human cell-based testing method so that we don't have to go through as much animal or failed clinical trial as we may have done before. So the US, which is known to be the biggest market for cosmetics and pharmaceutical industries, has yet to ban animal testing, but it is undoubtedly moving toward it. And in 2017, in September, actually, the federal EPA became the first governmental organization to actually sign a directive saying that the US will prioritize efforts to reduce and eliminate animal testing across the US by 2035. And so as we go on to understand what human skin equivalents are and what the bioprinting technology means for us in this area, it is important for us to know the principle of the 3 R's, which stand for replacement, reduction, and refinement. And this provides a framework for basically performing more humane and sustainable research by replacing and reducing and refining animal experiments with better alternatives. And really this principle that is affecting a lot of the areas of various biomedical research makes human skin equivalent models like the ones bioprinted not only sort of a solution that is that we believe in, but a solution that is becoming more and more pushed towards by regulatory guidelines as well. So with all that we have said, basically underpinning the fact that ethical testing is no longer a lifestyle choice, but soon rather to become a legal requirement, we can talk about what it takes to build and create the human skin equivalent. So what exactly is the HSE? An HSE is an engineered tissue, skin tissue, that is designed to structurally and functionally mimic the real human skin. And as you can see here in the diagrams and the H&E pictures below, an HSE begins foremost with the structural simulation of the stratified layers that our skin as a natural barrier exists in, all the way from the dermis to the epidermis. And if we actually take a look at the history of the HSE development, it goes all the way back to the 1940s. First, when the culturing of 3D human skin biopsies ex vivo began, just prior to the standardization of nutrient media. And these were the prevailing methods of research to study anything about skin. But in the 1950s and 60s, these skin biopsies ex vivo grew to be replaced by more, more accessible methods of research, which were mixed and single type primary 2D cell cultures, especially with the use of human keratinocytes, but oftentimes these were just one type of cells being used. And although 2D culture has been simple and reproducible, the relevance for 3D constructs became more and more evident throughout the 70s and 80s, as more and more publications came to show that 2D models have different results from actual human skin-based tests. So in the late 70s to the 90s, more models like the living skin equivalent that implement the dermis like collagen hydrogel with human keratinocytes came about. And we've also got technologies like electrospinning coming into the picture to create 3D scaffolds. And now today, in the 21st century, we see the implementation of 3D printing for use in biological applications to replace the hand-poured hydrogel matrix or electrospinning, because it provides a much more architecturally complex method for the production of 3D skin tissue constructs, because it takes the benefits of computer-aided design and realizes them with the use of multiple cell types and multiple biomaterials. And one interesting thing to note is that global organizations like the OECD have actually set up multiple guidelines for the testing of chemicals, such as TG431 or TG439, which basically are standard ways of assessing chemicals that cause skin corrosion or irritation. And these standard ways would be measured by existing in vitro test models using 3D skin tissues. These may or may not be bioprinted, but the fact that the OECD has already started providing these guidelines for the effective use of in vitro models tells us that the use of human skin equivalents is becoming more and more an effective and accepted model for human skin research. So to understand how we end up engineering human skin using the bioprinter, we must first understand what are the components that comprise the human skin. So you guys would be more experts than me in the Department of Dermatology, but just to briefly go over, we understand from the bioengineer's perspective that the human skin is basically structured in macro layers and micro layers that are comprised of significant cell types that make up what these layers function as. So for instance, we understand that the skin is composed of mainly two macro layers, which are the epidermis and the dermis. And beneath the dermis lies the hypodermis, which is composed mainly of loose connective and fatty tissues that then connect to the muscle and the bone layers beneath. And if we go deeper into each macro layer, the epidermis, for instance, is composed of mainly keratinocytes, which proliferate starting from the deepest layer of the epidermis, the stratum basilae, all the way up to the corneum layer. And these keratinocytes making up 90 to 95% of this layer, and the differentiation stages of these keratinocytes are what would need to be recapitulated in our engineered skin tissue to make it an effective and reasonable model for skin research. In the epidermis model, other cell types that we can make meaning out of are the rest 5 to 10%, which include immune cells and sensory cells, such as the Langerhans, the Merkel-Ranviers, as well as the melanocytes. And melanocytes present in the bacilli that produce melanin would contribute to skin pigmentation. And these cell types are also something that is meaningfully used in the construction of skin models, especially in the testing of age-related skin diseases or pigmentation-related skin conditions as well, which we will see later on. Now, the dermis, which is considered the core of the skin system, contains mainly fibroblasts as well as a lot of structures made with collagen and elastin fibers that make up the sort of the core characteristics of this layer. And the fibers that give the characteristic structure, the tensile strength, and elasticity to the overall skin give us a picture of what would be necessary in composing this layer as well. Make note of the collagen and elastin fibers because this would directly translate into the types of bioinks or biomaterials that you would end up using mixed with fibroblasts to create this dermis layer. And finally, the hypodermis, also called the subcutaneous layer, is a layer directly below the dermis, as we know, and serves to connect the skin to the underlying fascia of the bones and muscles. And this is not strictly a part of the skin, some may say, although the border between the hypodermis and dermis may be a bit difficult to distinguish. But basically, this hypodermis model of the skin is often an interesting portion that especially pharmaceutical companies are interested in mimicking because of its meaning toward the development of models for testing subcutaneous injections, or are interested in how perhaps certain drugs penetrate, how well certain drugs may penetrate across the epidermis, the dermis, and all the way into the muscles or fat, the muscles or the bones. So this hypodermis layer could also be of consideration in the engineering of your human skin. Now, traditionally, if we look at how any tests for skin have been done, any test of compounds for skin have been done, traditionally they have really depended on animal tests and 2D cell culture methods, as we are familiar with. However, a lot of studies over the years have clearly demonstrated the lack of these models to fully recap what actually happens in skin. So if you take a look at the left-hand side publication, this talks about the limitations of one traditional animal test for cosmetics, which has been the Dre's test for skin irritation using rabbit models. This one in particular, if you can see the tables below, has shown that animal models can basically lead to an incorrect labeling of chemicals due to their inability to predict what actually happens in the human skin. As shown as table 4, of 16 tested chemicals classified as irritants in rabbits, only 5 were found to be irritants for human skins. And also for chemicals to which the rabbit test exhibited 100% sensitivity, it turns out only 55% of non-irritants were wrongly labeled as irritants when tested with the human skin model. And in the same way, a comparison of 2D cell models to 3D, as shown on the right-hand side publication, has shown that the culture of skin cells in 3D tend to exhibit a greater survivability against cytotoxic agents. For instance, to the same given dose of hydrogen peroxide or silver nitrate, 3D cultures were shown to be twice as likely to survive as 2D. And we can sort of imagine why this would be happening because of the types of ECM environments that the 3D cell cultures would end up developing in the dimensions that they live in, as opposed to 2D growing on a flat surface in Petri dishes. And so this study has not only shown the difference between 2D and 3D skin models, it has also shown that cells in co-culture rather than monoculture were better at surviving some of the stresses represented by the cytotoxic agents. And this has brought home the necessity for building increasingly more complex tissues for better modeling than relying on monocultures or single cell type cultures that we are familiar with. So actually, against the limitations of a lot of these existing animal models and existing 2D models, various 3D fabrication methods for human skin have been developed over the past decade. And some of these most common ones, which some of you may already be familiar with, include the following. There is the technique of freeze drying, which basically relies on randomized scaffolds preparation that goes through a basically sublimation process where the frozen water in polymer nanocomposites is directly converted from solid to gas state and removed, resulting in these pores that you find. And then you've got solvent casting, salt leaching, which depends on the addition of salts to a polymer solution and hardening that, and followed by leaching of those salts by submerging it in a solution that dissolves the salts away. You've also got electrospinning, which is basically the creation of nanofiber mesh by applying high voltage electrostatic forces. You have decellularized pigskin for the combination of human cells to this decellularized scaffold to serve as ECM scaffold for 3D skin models. And then you've got spheroids. These are all multiple steps ahead of the existing 2D keratinocyte or fibroblast models that we may have used However, they are not without limitations themselves. For instance, for a lot of these methods, it is difficult to control the cellular compositions and the macrostructures that the actual human skin exists in. There are also some processes like freeze drying and solvent casting go through pre or post processing steps that may have adverse effects on the scaffold preparation that eventually gets exposed to cells. And certain models like the spheroids or the reseeding technology using B-cell pig skin may end up with certain limitations like necrotic pores, which basically means the lack of delivery of enough nutrients to the core to the core areas of these cell aggregates, because you don't have the ability to mimic vascular systems that our human skin originally has. And so if you actually see the picture on the right-hand side below, this is a picture from a research lab in Singapore comparing the human skin equivalent with melanocytes made using the bioprinting approach versus a manual casting method by hand. And what they've seen is that by being able to automate and evenly spread the cell types using the 3D bioprinter, they were able to obtain a perfectly circular shape with an even distribution of the substrates, resulting in a certain physiology. Whereas in the manual casting approach, the uneven distribution of the substrate they were trying to make into the engineered skin led to a disfigured shape that ultimately also resulted in abnormal pigmentation in the center. So these are some images showing how I would say the core benefits of automation and even distribution of cells using the bioprinter what effects that could bring into our physiological model results. And so given what we've said so far, this is what the human skin equivalent engineering process might look like using the bioprinter. And these are according to images taken from the ROKIT Healthcare's R&D team. As you can see, the stratified layers of the human skin equivalent can be realized onto well-played formats, allowing the use of human tissue models for high-throughput assays like drug screening. And these stratified layers of the human skin are realized by taking the advantage of CAD, computer-aided design, and basically translating them directly into living 3D structures made with living cells and biomaterials that mimic the ECM environments of the human skin. So in the second half of this session, I would actually like to go through what bioprinting exactly is, how the workflow actually goes, what are some of the biomaterials that are considered for building these types of tissue models, and finally, so what have been the applications of such bioprinted human skin in real life? So bioprinting as a technology is getting a lot of attention in mainstream research only recently. The origins of this technology actually go back 2 decades, so it's not really a baby step technology anymore. In fact, the number of publications around this technology have been exponentially growing since 2000, and today there are thousands of such publications testifying to the use of this technology across tissue engineering, biomaterial development, regenerative medicine, and even biomedical device engineering like in soft robotics using hydrogels. Here in these tables, you can actually see a list of publications hyperlinked And these all have to do with the ideal choice and combinations of cells and biomaterials for tissue-specific applications that have been identified in these journals by different groups. And we've put together these tables basically to show that bioprinting at its core is a platform technology that allows you to choose the types of cells you want to study, the types of bioinks that are ideal for those cell types, and put them together to create on-demand 3D human tissues that can be used to have your research move forward in between the 2D in vitro cultures and in vivo animal studies or human studies that we traditionally rely on. So why do we call the technology often not 3D bioprinting, but 4D bioprinting? It is because 4D bioprinting is a process in which cells, living cells, biopolymers, and growth factors are combined to create tissue-like structures that not only imitate native human tissues, but also may function like one. And because these living tissues are often then incubated to further proliferate, mature, and change over time, this is where the dimension of time makes the technology 4D rather than 3D. And the 4D bioprinting technology consists of largely 3 components. These are the biomaterials, the bioprinter, which is the hardware, and the design component, which is the software. So first, let's talk about the biomaterials. Unlike the traditional 3D printer, which uses hard plastics, metal, or synthetic materials to create non-living structures, a 4D bioprinter uses materials that are biocompatible, biodegradable, and often derived both from natural and synthetic sources. As you can see here in the table, I've outlined some examples of what I mean by naturally derived, synthetic, and composite biomaterials that often get used in the bioprinting process. Naturally derived include materials we're already familiar with, like collagen, elastin, chitin, etc., that come from the ECM environments of animal or human cells. We've also got alginate, silk keratin, or cellulose, which come from plants and seaweeds and insects, these natural organisms in biology. And we can also have materials like hydroxyapatite, which naturally comes from mammalian bone. Synthetic biomaterials, on the other hand, are man-made, and these are oftentimes biodegradable polymers exhibiting enough strength and elasticity to mimic the scaffolding environments of human tissues, and may often have references of use in already FDA-approved medical devices. And finally, composite biomaterials could combine natural and synthetic materials, often because either one of them either doesn't have enough mechanical strength or biochemical properties that living cells are happy in, or because they either one may lack some ability to have printability in the printer. So please note here that bioinks, which is a term often used in the bioprinting world, basically refers to biomaterials that are combined with cells. And these biomaterials often tend to have the form of hydrogels, which are supposed to mimic the ECM when you're trying to print cells outside the body. And these hydrogels, as they encapsulate the cells, are supposed to protect them from shear stress of printing and also provide the cells with nutrients, hydrations, and the overall physiochemical support when they are existing in these bioprinted tissues outside our living bodies. And when selecting materials for bioinks, there are several key criteria you want to remember. And these criteria can be basically summarized into two broad categories. One is the bio inks should be able to extrude out of nozzle tips with enough dilation kinetics, shear thinning properties, as well as viscosity. And number two, the bio ink should also be biocompatible to uphold high cell viability. And this would, of course, be defined by how mimicking are they of the human ECM components most oftentimes. So now that we've talked about the biomaterials, what is the hardware, the bioprinter, that makes use of these biomaterials into 3D structures? There are various types of bioprinters today, from inkjet-based, laser-assisted, stereolithography, and in situ methods. But I'm going to focus on the extrusion method because this basically covers about over 70% of the existing bioprinting methods outlined in journal publications today, most often used. One key component of a bioprinter hardware is the printheads, which should be able to print both hard and soft materials to really make something a bioprinter. And there are two ways that the printheads can print. One is scaffold laden, and the other is scaffold free. The scaffold laden often is composed of hard materials, like, for example, PCL, PLA, that make up these frameworks upon which cells can grow, making use of them as the blueprints for growth into 3D tissues until the scaffolds start to degrade away and leaving thus room for the tissues to fill up those space. Another method is scaffold free, where you don't make use of any harder materials, but you make use of soft materials like hydrogels. And you simply encapsulate those cells in these hydrogels and print them directly into a 3D structure. Of course, these hydrogels would have to have some capabilities to stack on top of one another in the layers, meaning that these hydrogels would often be cured or cross-linked using methods like UV, temperature, and chemical additions. Another key component of the bioprinter is the chamber's ability to mimic a biosafety cabinet, because after all, you're trying to print and deal with living cells. To optimize cell viability and functionality under the stress of printing, the chamber of a bioprinter often has UV disinfection capabilities, the HEPA filter, and bioreactors like a CO2 incubator to provide the optimal environment for cells so that they actually function even after you have printed them. And finally, the third component of a bioprinting platform is the design, meaning the 3D models of the objects we're trying to print. 3D model files are known as STL, and these can be obtained either by manual creation using design software like SolidWorks, or they could be derived from CAD MRI scans of physical human body parts or whatever tissue structures you want to mimic. These STL files then get processed with what's called the slicing software that basically translate this design into standard machine language called the G code. And the G code is going to describe for us how a bioprinter should print the job using information on XYZ positioning, the printing speeds, the infill patterns, etc., to describe what you have, the picture you have given to the printer. And the example images below show the difference between an STL object file and G-code variations, where the STL object file on the left, it just describes some type of three-dimensional structural image of a square, whereas G-code instructions would describe that 3D image into certain patterns that the printer will then print, such as the variations in infill density that the same STL image can be translated into, as you can see in the pictures below. And now that we understand the components, we could understand the bioprinting process. And this process principally involves 5 key steps, which are the preparation, printing, post-printing, evaluation, and application. So preparation involves designing the experiment with a clear identification of the problem to address, as well as the right biomaterial cell types and 3D models that you're going to use. For instance, if we were to use the human skin, you would need to understand, like I said before, what are the biomaterials that exist inside the human skin and what are the cell types that comprise it. Now, printing is the actual process in which materials that you have identified before are loaded into the printer, like the cells and the ECM biomaterials. Then the 3D models that you've designed are sliced into appropriate printing instructions. And the bioinks that you have loaded into the printer are then deposited out of the nozzles. In the post-printing process, whatever you have printed out is going to be processed so that it actually maintains a stable and functional structure for the tissue that you have tried to mimic. For example, if you are to print fibroblasts or keratinocytes into a hydrogel of collagen, you may have the concern of the collagen just crumbling down instead of holding its 3D structure. So in that way, in that case, you would use cross-linking methods such as temperature, raising it to 37 degrees to harden the collagen, or you may use UV light in order to cross-link certain types of collagen that may be that may contain methacrylates, allowing them to respond to UV light of certain wavelengths to cross-link. Then in the post-printing process, you would also allow the cells to perhaps differentiate if you are using stem cells in order to reach the final result of tissue that you want to create. You may also, for skin especially, you may make use of certain post-printing processes like air-liquid interface procedure to make the keratinocytes differentiate into the corneum layer. In the evaluation and application stages, we take a look at the structure, the morphology, and functionality of the tissues you have printed and apply them to certain application areas such as in vitro disease modeling, in vitro testings of compounds, or even in vivo transplantation. So here is a sample bioprinting process that is applied to the cardiac patch engineering. And for the sake of time, I'm going to skip over this, but you would be able to take a look at this in your own time using the recording that we will provide later on. So in the context of all of these, let's now get to the heart of the applications. And slides in the following are going to be basically summaries of publications making use of the bioprinted 3D human tissues. But for more details on these publications, you can take a look at the references we have put at the bottom of each slide. And I'm going to really quickly go over these because I just want to leave time for you to ask questions at the end to learn more about these. So what are the applications of the HSE today? Really, these applications are numerous as far as they go to the studies of basic human skin physiology and the reactions of human skin to the introduction of novel compounds. But one of the most largely used application is in the testing of these models for toxicological evaluation of drugs and topical agents. So corrosion and irritation tests with the HSE are some of the most widely characterized, especially with the OECD guidelines, titled TG 431 and 439. And basically, in this area of application, you can use the HSE to apply the substance onto its surface and check for toxicity within 4 hours of its entry, especially from the rate at which the cells die off in the engineered human skin. Absorption and penetration, or otherwise known as permeability tests, are also done using the HSE. Here, researchers would measure the amount of transdermal moisture loss in the HSE through the immunostaining of moisture-related proteins. The sensitization test can be used for experiments related to the immune system. Maybe, for example, hypersensitivity to certain substances, like in the condition of erythema. And this can be done by exposing the surface of the HSE to allergens and then identifying the immune reaction mechanisms by downstream analysis of that skin tissue. And with an HSE made by mixing melanocytes with the keratinocytes, you can also perform lightening or a whitening test, which basically tracks changes in the melanocytes in the engineered human skin, like you could see in the picture on the right-hand side below. The changes of color and the concentration of melanocytes over time. The HSC also finds applications in the pharma industry, from novel drug screening to drug delivery mechanism studies, by studying the penetration of the particular drug that you are trying to study through the epidermal and the dermis layer of the engineered human skin. It's also possible to judge the presence or absence of toxicity with the aid of phototoxic substances and applying them to the engineered human skin. And it is also possible to check the degree of aging of the skin by conducting UV transmission tests. Aging skin models can be made by manipulating the dermis layer of your engineered human skin with different cell types representing different age groups. And basically, with all of these models, the great thing about bioengineered human skin is that instead of the 2D cell cultures that are too simplistic, and instead of animal models that may be too expensive, you can sort of find the right balance with the 3D bioprinted tissue models, which can be more architecturally and compositionally complex because of the design and the biomaterials you can input into these tissues. But at the same time, it can be much more sustainable in terms of costs, because you no longer have to rely on outside resources, but you can make these tissues on demand with a standardized protocol that you develop using the automation device called the bioprinter. Beyond these in vitro tests that we've talked about, the HSE is most often used as a disease model. And here we see some figures from publications showing models for cancer by the induction of or hyperintroduction of melanocytes into the engineered skin to represent melanomas. And you also have a figure from a publication showing a wound healing model where engineered human skin was incised with a laser, with a pointer laser, and then it was left from 3 hours to 72 hours to show how the skin healed after this injury. And other models of skin disease include psoriasis and atopic dermatitis, which are examples of desensitization tests that I talked about before. And these have been created by exposing regular human skin equivalents into cocktails of cytokines that then cause these living 3D bioprinted human skin tissues to transform into these disease models. And in the same logic of things, by the manipulation of cell types or by the manipulation of introduction of hair follicles, for example, you could also create age-specific skin models or hair versus hairless skin models as well, as demonstrated here in these publications. And so in the last few minutes, I'm just gonna go over what ROKIT Healthcare and our users have done using the bioprinter to create the human skin equivalent. And these are actual H&E pictures and data from area function tests and irritations tests that have been done on 3D skin. Figure 1 shows the histological characterization of the engineered epidermis version. And as you can see from the different morphologies of the cell types, as you move from the stratum basilae all the way up to cornea, you can see that structurally the 3D tissue, the 3D epidermis is able to mimic what we would see in the actual human skin. And from the immunohistochemistry results of proteins such as CK10 or P63, you can identify that these keratinocytes are proliferating where they should in the micro layers of the epidermis. And with the barrier function test and irritation tests, these have been done according to the test guideline given by OECD. And basically, these 3D human tissues are exposed to the cytotoxic agents such as Triton X10, 1% Triton X10, to show how much of the cells in the engineered skin stay viable after exposure, in order to compare it to the actual, standard human skin, to see whether the skin tissue actually serves the barrier function in delaying the penetration of the cytotoxic agent to the cell types. And also irritation tests have been done using already known non-irritant chemicals and irritant chemicals according to the OECD guidelines to show that the engineered human skin exhibits characteristics that we expect from the standards. And here, by a user of the Dr.INVIVO Bioprinter at the Seoul National University in Korea, they have demonstrated the ability to create adipose tissues that could actually combine with skin using biodegradable materials called the PLCL mixed with adipose-derived ECM. And they have shown that these custom shape and custom dimension adipose patches have the ability to promote vascularization as well as adipose tissue regeneration in the in vivo models of mice. But most importantly, of course, some of these applications of engineered human skin may really bring huge benefits when they could be translated into medicine for the purpose of patient benefits. And here in this application, I would like to present to you a way that the bioprinting of skin-like solutions is making changes in the creation of novel diabetic foot ulcer regenerative solution. As you know, chronic diseases like diabetic foot ulcers have really remained in medicine with non-regenerative treatments over the past 20 years. Many of them rely on single component dressings such as collagen dressings, or they rely on treatments like negative pressure wound therapy that only seek to reduce symptoms but don't really get at the core of the issue in the ulceration of skin. So here in this application developed by ROKIT Healthcare and a diabetic foot ulcer specialty clinic in India, we have created a process in which the bioprinter could be used to use autologous MAECM, minimally manipulated autologous ECM bioinks that are prepared by the extractions of adipose tissues directly from patients. And these autologous solutions are then printed into customized patches that could then be applied to the defect area, basically to prime regenerative processes from the surrounding environments. And from this process, we have seen through various clinical studies in India, Korea, and further on in what we wish to reflect in future studies in the US, Turkey, and Italy, we have shown that these ulcers that have remained open for more than 6 months to 2 years closed within about 4 weeks using these customized patches of autologous solutions. And this is where we see the bioprinting technology really headed in transforming not only scientific research, but medical therapies for a lot of the chronic skin conditions that that scientists of dermatology would try to seek to address. And here is a short video of what that scan to 3D print system looks like using the 3D bioprinting process and the computer-aided design help us to create novel solutions for skin diseases using autologous patient solutions. So I'm just gonna fast forward the video to show you what that process looks like. And you can take a look at this more in detail later on. So I'm going over time a bit. So let me just quickly go over the fact that while we have focused on talking about skin today, bioprinting is a versatile platform. And as I will show you here in a few minutes, various published articles by our bioprinting users, the platform finds applications not only in skin engineering, but also in various soft tissue engineering, development of disease models, and developments of even medical devices. So here we see an example of the use of bioprinting in creating 3D vascularized tumor models for drug testing. Here, creation of an elastic nerve guidance conduit using 3D printed collagen hydrogels on a nanofiber membrane. Printing of strontium substituted hydroxyapatite scaffold in order to create bone regenerative matrices that were implanted into in vivo models for showing efficacy. Here is an example of the use of bioprinting to create muscle models, which are very rare in today's research area for drug efficacy and safety testing, especially in well-played models for high-throughput assays. The bioprinter has even been used to create novel drug not only drug delivery, but drugs themselves, like in this example, where the hot melt pneumatic extruder of the bioprinter was used to print QR-coded oral dispersible films, which are not only easy to swallow, but that they also encode information about patients, making the way for smart drugs. And then we've got bioprinting being used to create versatile scaffold platforms to represent different progressional stages of ischemic heart disease. So you can potentially make different models of the heart disease with the heart patch. You could make a bioresponsive device for microbial metabolism studies using, a specific deposition of microbes into a 3D printed structure. And finally, people have also made use of the bioprinter using hydrogels and thermoplastics to create thermal therapeutic devices that can heat as well as cool. And so much more. And so our goal as a company and also as a bioprinting community is really to inform researchers interested in using the bioprinting by feeding, by feeding into each other across industries and across academia, the knowledge that we have gained in different realms of the biomedical world. And so we can talk about these later on, but some of the technological platforms that ROKIT Healthcare provides for the benefits of researchers include this type of system, a clean bench bioprinter system that allows you to print both with hydrogels and cells, as well as polymeric filaments and pellets, so that you could print both soft and hard tissues inside a biosafety cabinet. But also moving on from that, we are also providing a system that we call an organ regenerator that basically combines not just the ability to print soft tissues and hard tissues in a biosafety cabinet, but also gives, most critically, a cell culture environment through the inclusion of an incubator that can control the CO2 levels, the oxygen levels, as well as the humidity levels and the temperature, so that the printed tissues that you've got are given a optimal cell environment for growth and proper functionality. So to give you a picture, sort of an online demo of what a bioprinting system would look like, here is an example of a Dr.INVIVO 46 allowing you to create a structure with up to 6 different biomaterials at once. And you've got an incubator built in that allows you to control the temperature at 37 degrees and CO2 and humidity levels that are mimicking of the optimum mammalian cell culture environments. And of course, the HEPA H14 filter for clean air is also available. And you've got a bioprinter that is able to also sort of serve the function of a liquid handler in order to help you create high throughput assays with cells and tissues of your interest. And the tissues and cells that you could use are made available by the different types of print that you can make use of. Sort of the same benefits that we take from the Dr.INVIVO 42. These include the hydrogel dispensing modules, as well as the filament and pellet and powder dispensing modules as well, for accommodations of both soft materials like alginate, chitosan, collagen, fibrin, etc., as well as hard materials like ceramic particles, hydroxyapatite, polyurethane, and other synthetic biomaterials like PLA and PCL. And so here is what the sort of the UI of the system looks like. allowing you to control the bioprinter from a tablet or a mobile phone. But at the end of the day, the key take-home message is that bioprinting brings essential qualities to research that traditional techniques may lack. And these include automation, physiological relevance through complex architectural mimicry, as well as on-demand fabrication. And with these in mind, you are able to basically generate biomimetic structures and tissues without having to depend on model systems that are existing that may be either too expensive or not ideal for the purpose of your research. And just imagine that if we could have such biofabrication centers or bioprinting platforms all across the world, we could imagine the technology has the potential to completely transform regional biomanufacturing value chains, really giving the power of on-demand fabrication to the researcher themselves. And not surprisingly, in fact, bioprinting centers of excellence have already been arising at the international levels over the last few years already. And companies like us and communities of our researchers collaborate a lot with these centers to move the technology forward. And as the last words, I would like to leave you with this image. The era we live in today is really an era of tissue engineering and regenerative medicine. And in this era, we believe that bioprinting is not just the revolution that's underway for the way we create model systems for answering basic biological questions. It's actually a revolution in the way we practice medicine. Instead of using systems that have relied on treating symptoms using monotherapies or small molecules, our vision is that the bioprinting could harness the body's own healing potential inherent in the stem cells, and it could also harness the regenerative potential that comes from simply structurally mimicking the human tissues that exist in our body most with the best methods of biomimicry. And the future of medicine is already being realized today by those who are pioneering this technology in various disciplines of science. And we look forward to continuing to support with these types of knowledge sharing. So thank you so much for being patient with us throughout this 1 hour and for sharing the passion and willingness for innovation with this technology. And now I will open up the table for any questions. Thank you so much.
HSE, the human skin equivalent. So from a potential user point of view, I have two, well, actually those two questions are related. So, how long the HSE can be cultured? You know, this question is related to, you know, if you are performing some chronic experiments. So how long these tissues can be cultured without, you know, significant changes in the quality of the tissue. And then the second related questions is the stability. For example, this is more like a reproducibility question. So if I order, you know, a HSE today and then kept for like 2 days or weeks in whatever, so how do they have to be like every time freshly printed? So those are my questions.
Okay. So in the typical engineering process for an HSE, consider that these are living cells printed. The number of days that it goes through until it's ready for use is about 14 to 18 days. And in these days, the skin cells are cultured in air-liquid interface, for example, in well-plate formats. And they are cultured for about 14 to 18 days until we can say that the keratinocytes have been terminally differentiated into the corneum layer that represents the topmost layer of the epidermis. This is the standard protocol that most people follow in the construction of human skin models. And you talked about how many days are the tissues able to be cultured after, for example, freshly printing them or ordering them from a provider of HSE until you can use them for your research. Again, with fresh printing, you would, with the standard process of engineering these models, you would wait 14 to 18 days for them to grow and mature before you apply them to like in vitro toxicity tests or basic skin physiology tests. With the ones that you order sort of off the shelf from providers of HSE, I understand that they often recommend you to leave them for about 2 days in the cell incubator for them to sort of acclimate to the environment before use, so that any dead cells sort of can be disregarded and any live cells in that HSE can proliferate and sort of be functional for use after getting used to the cell culture environment that they get exposed to.
How long can they continue to be cultured? Is that variable on the experiment?
Oh,
or?
after the 18 days, sort of after the 18-day mark?
Yes, I mean, when someone orders and then you, the commercially available, say the Epitem, and then you acclimatize for 2 days, and then you say you have to do a long-term culture. Can you go on for 3 months, 2 months, few weeks?
Oh, after that's a tricky question for me to answer.
We don't know the answer to that, I guess.
The thing is, most downstream applications I've seen are done after I guess after about the 2-day incubation mark, after the 18 days of culturing of the engineered skin. But some assays that I've seen, for example, have done up to a 72-hour assay, like in the publication I showed you before. So I would say about the mark is 2 to 3 days after the fully mature engineered human skin culturing.
But I guess one would have to really test it in their experimental condition to see how long they can actually continue to survive in culture.
Right. I mean, I would think that some of the basic questions we ask in regular 2D cell culturing, where where there is a maximum mark at which we would no longer want to culture those same cells in the same petri dish because of the lack of nutrients or etc., or overcrowding of the cells in that same platform. Those same basic questions and answers would apply to the bioprinted skin.
Yeah.
Okay, and to the point on reproducibility that Dr. Chang asked, I guess there should be very little or no variation because these are highly standardized methods of printing. They use the same type of material and same amount of biomaterials to recreate the structure. So there should be reasonable uniformity between different batches, right?
Yeah.
Well, so from toxicology point of view, you would imagine, we all understand the 3 R's. We definitely want to replace or reduce the animal usage. But, a lot of the toxicity tests are actually done in subchronicle or chronicle. If a replacement, or you call it HSE equivalent, can only be, I'm not saying it can only be used for 2 days, but if it cannot use for long term, so that would be a little bit difficult. Or maybe it's an opportunity for you guys to to develop something can be used for long term, so that way the animal can be totally replaced. Well, just my naive point of view.
Yeah, that's a good point. Yeah, I guess I will talk since I'm maybe it might be a question I also may want to ask the actual skin R&D team at ROKIT Healthcare to properly address what types of long-term time points have researchers actually used this HSE technology. I will get back to you guys after asking the team as well.
Anyone else has questions? If not, I'd like to ask you, Dr. Chang and others, do you find any potential for application in your research projects? Any potential for bioprinted skin tissue?
Okay, so I'm not. I'm gonna cue Dr. Mukta here. So Dr. Mukta will be the one with the most experience with the reconstructed skin tissue. You know, the 3D culture and rebuild the fibroblasts and the keratinocytes. But to me, I definitely think it's gonna be a great way to you know, it's better than 2D, and you know, it's definitely has a lot of advantages. That's why I'm very interested. But I think Dr. Mukta might have a more to say on this. Dr. Mukta, you're muted. You're muted. Oops, it's muted again.
No, muted again.
Yeah, I think you double clicked it.
Can you hear me?
Yep.
Yes, sir.
Yes.
Nice to meet you.
I agree with Hao that the technology as it's developing has a lot to offer. But for short-term application, it's not really evident what can be done. To answer, I think one has to dig deep into the system to get a handle on this technology for its benefit to, I see, obvious advantage each of our research.
Good to know. Thank you. May I know what is your specific area of interest within the dermatology space?
I have been studying the use of natural products for treatment of psoriasis, for treatment and prevention of cancer. So in psoriasis world, I see applicability, but in cancer field, I don't see much of the applicability. So
Did we not have a couple of publications on the use as a cancer model? You showed a few, I think.
Oh, for me? Yeah,
Yeah.
I think I showed a figure from a journal publication making use of melanoma, basically melanocyte concentrated skin tissue models for melanoma studies. But yeah, there of course, as with all technologies, there is no I would say from my experience on the bench as well, there's no sort of one silver bullet or perfect solution to address all the challenges we have. But what the bioprinting offers is some of the even some of the most common challenges that we currently have with the most familiar models of research, such as 2D cell culture or 3D spheroids, or even animal models, some of them are addressable using developing technologies like the bioprinter, which focuses on bringing automation to the lab. And so some of these addressable challenges we can overcome by making use of the technology. Other sort of tissue-specific, sort of biology-specific questions would probably need to be addressed by sort of having better ideas about the selection of cell type, selection of the ideal biomaterials to make compositions of these engineered tissues in the long run. But what I can say is that in the market today, as you all know, there already exists several companies who have commercialized 3D, or 3D, though manually created human skin tissue models like the epidermis, the dermis, or the full thickness, and have registered them with the OECD, making evidence of the ability for these engineered 3D skin tissue models to mimic how actual human skin might behave to certain irritants or non-irritant chemicals, or to certain, basically to certain compounds that they get exposed to. And that is why these HSCs are already sort of revolutionizing the research methods in cosmetic industries. But of course, there is definitely more room to go in the pharmaceutical industries and more.
Also, to add a note on that, the platform presents an opportunity for innovation that you as researchers can bring in, and that also ties well with the fact that when you seek a fundability of your research, this can present and position itself as a novel approach towards an unmet need of better model systems other than the conventional models or animal models. So it also drastically increases the appeal of your research for potential funders. And as a company, Dai, maybe you should also reiterate that fact that ROKIT is not just a printer manufacturer, but it's more a well-rounded regenerative medicine company. So you also get a lot of support in terms of the experimental design that might be kind of a custom needed for your own research, apart from the instrumentation itself. Plus also the whole bunch of biomaterials, especially the whole ECM humatine, which can be delivered as more cell-specific variants. So there are many benefits here that we haven't had the time to go over.